All right, welcome to the TILOS ICSI Joint Center. So today we're thrilled to have Professor Michael Mahoney visiting us from UC Berkeley. Michael is at the University of Berkeley Department of Statistics and International Computer Science Institute. He is also currently an Amazon Scholar as well as the head of Machine Learning Analytics Group at Lawrence Berkeley National Lab. He works on algorithmic and statistical aspects of modern large-scale data analysis. Much of his recent work focuses on large-scale machine learning, among many other ones. And he was also on the National Advisory Committee of Statistical and Applied Mathematics Science Institutes. He was also on the National Research Council's Committee on Analysis of Massive Data, organized some institutes many events and so on and so forth, among many other awards. But I think maybe let's leave the time to Michael. Let's welcome Michael Mahoney.
All right. All right. Well, thank you. Lots of great things, except even after all these years on Zoom, I still can't figure out how to get rid of these things on the side. So, all right. Well, thanks for the invitation. It's nice to come down here. And if you're on Zoom, I don't see you. So if you have a question on Zoom, type it in and hopefully someone will interrupt. And if I happen to wander over here and mumble so you can hear me on Zoom, then speak up or holler or something. So don't be shy on Zoom about hollering. So I was asked to come down here. So thank you for that. And I said I could talk about one of a couple things. It could be this or this. And they said, why don't you do this one? This sounds like a good title. So I have a confession to make. The title talks about foundational methods for foundation models for scientific machine learning. So I don't actually know what I'm talking about because I don't know what a foundation model is, actually. I can tell you what different people say it is. And I think understanding the delta in that space is an interesting thing. And I'll stick a flag somewhere and make a claim. But I don't actually know what they are, right? And so I think it's sort of hard. Maybe this is not a general political commentary on this day and age. This is a scientific statement. But I think it's hard to change anything when things are sort of in place. You need a bit of anarchy. And so I view foundation, this is a statement of foundation models. I view the foundation model as a way to do that, as a way to try and do something very different on the scientific front, methodologically. So I first got to Ian as part of the tripods program, which is an NSF thing to do transdisciplinary stuff, math and computer science and physics. It's very hard to bridge those gaps. The timing just happened to be right. And we had good ideas, but good ideas get killed if the timing's not right. And so you have these things called foundation models. And I think there's a lot of science areas that are doing very narrow things. And so this is an excuse to think more broadly about just sort of scientific stuff in general. Because, if you think back, timescale 100 years or more, science used to do stuff by pencil and paper and then experiment. Then computers came along. It was a painful process, but now computers are front and center in the way scientists use things. And now the biggest advancement sort of on the technology side for science, accelerators, machines, they're all bigger and better, right? But following a general trend. But the thing that sort of wasn't there 20, 30 years ago is all this machine learning stuff, whatever that means. And so now it's achieved sort of a crisis point where you can really start to think of it with these foundation models. So by foundation model in particular, it's not a language model. It could be, but it could think much more generally, all right? And I think partly this gives you an excuse to think about foundational methods. And just think back to TILOS or tripods or the photos. Even if you don't care about science and you just want to do machine learning theory, this is a great thing to know about because you can learn this stuff. You can go back and beat up on the machine learners and say, here's a way to think about other things a little bit more broadly. Because this is sort of a hydrogen atom or a Drosophila. If you know what those are, you're a scientist. If you don't, you're not, right? So hydrogen atom and Drosophila are very sort of model systems to think about machine learning and data-driven methods and domain-driven methods just much more generally. And I can't switch my slides. So, okay. So physics-informed learning is, and think broadly in terms of physics. I don't want to get into physics versus chemistry versus civil engineering. So computational science is an important tool to incorporate basically physical invariances into learning, lowercase l. I don't want to get into arguments about that. Until recently, it was really just not present in machine learning. So I do a lot of stuff in theoretical computer science and theoretical statistics and applied math and so on. But I've never taken a class in computer science or statistics, right? So my degrees actually are in physics and computational statistical mechanics and moved into this area after that. So sort of informed stuff in the back of my mind. And one of the interesting axes is that computational science scientific computing is something that can really, in some very strong way, analyze past events and look into the future. And so think of it from a machine learning perspective, right? Time series are sort of a hard thing to deal with because it doesn't fit very cleanly into the empirical risk minimization setup because you have this non-trivial correlational structure across time. A first-class citizen, probably in your life, certainly in science and differential equations, is time, right? So it's strange to jam everything into a very static setup, given that you live in time. And so it can look into the future. And it does that by distilling out sort of very basic things, the canonical examples, Newton's laws. You press the Newton law button, turn the crank, and you can predict eclipses 10,000 years from now. So, it's known the exact date and time 10,000 years ago, whether there'll be an eclipse, which is sort of remarkable if you think about it, right? This is seemingly pretty out of domain, right? So this is not tomorrow. This is, okay, so how does it do that? And I think it does that because it structures theory in a very different way, and it asks different types of questions. And this is useful because it really presents a way, I think, to complement a lot of the data-driven stuff and domain-driven stuff. Because I think scientists sometimes feel very emasculated and say, oh, ML is doing everything, you just press the machine learning button. But of course, in parallel, they complain that industry puts a lot of money into this. And the question is, where does industry put the money into it? The industry, aside from hardware, industry is putting money into it, into people. And those people spend all their time fiddling with parameters and figuring out how, in fact, to get this to work. Should you just do a convolution? Should you do attention? Should you convolve in this way? Should you convolve in that way? Should you cook features in this way? So they're really doing a lot of domain insight, but in very sort of narrow ways. So think a little bit more broadly. So I think to make further progress in scientific ML, you need to incorporate some of the ideas from machine learning, but also to make further progress in a lot of areas of machine learning and just machine learning theory and foundations, it's good to think about these things. Because not thinking about these things and just thinking about scaling compute, you get into all sorts of problems that are secretly numerical analysis or scientific computing in disguise, right? Machine learners are better at branding, so they have exploding gradients and vanishing gradients than condition numbers and well-posed problems in numerical analysis. But really, they're posedness problems under the hood. Right? So what is a foundation model? I told you I don't know, but I'll tell you what different people say it is. Can we hope to train something for scientific ML? What might that mean? Does incorporating physical knowledge help? You might say, yeah, obviously, hopefully a little bit, but if you're not careful and you cook in a little bit of domain insight, either because you know more about the domain than the ML, or you don't do it just the right way, you can do more damage than good. And so can you avoid that? Maybe some foundational questions, probably in the interest of time, I'll have a little bit less to say about implementations and applications, but I'll gloss through some pretty pictures just to sort of prove we think about that stuff too. But I'm glad to talk about any of that stuff also, because there's particular implementations that give you a whole pipeline. I'm at Berkeley University, and so, in university scale compute, it's large conditioned on universities, small conditioned on industries. Machine learning analytics group at LBL, so you have access to the supercomputers there. So again, larger than university, but still little of industry budgets. But implementations that address many of these particular questions, and applications in a range of different areas. And I'll give you sort of a hint of some of that. Okay, and then looking forward. What's a foundation model? Okay, so I told you I don't know what it is. A foundation model is a foundation. Right, period. Nothing else. Stanford wrote a 200-page report to say a foundation model is a foundation on which you build things. Right? So who's read that report? Okay, come on, you guys. So I've been giving this talk for a year. You saw this, come on, you guys. This was December 2024. V1 of this was, I think, April 2024. I think, I've asked that question for a year, and I think 3 people have raised their hand and all that. I mean, you are forbidden to use the F word, foundation model, in public discussion if you haven't read that report. Okay, so that's the new rule. Okay, so 200-page report. You're forbidden to use that word if you haven't read the intro to the report. How about that? All right. So a foundation model is a foundation upon which you build things. So I don't want to say that's 100% right. You can quibble about details of the report, but if you haven't read that, you're just shooting in the dark. So it's built using well-established principles from ML, supervised learning and transfer learning and these sort of things. I think you should think about this as a new paradigm in ML, because these are general purpose models that are reusable infrastructure instead of sort of one-off solutions, which is the history of the way I have one particular problem, one particular data set, build a one-off thing. Building foundation models is highly resource intensive. Adapting them to a different use case is pretty easy. So I flew in last night on Southwest. I oftentimes take United. Flew in on Southwest into the airport. I love coming into San Diego because you come right over the city. And I could look out the window and I could see that there was an airport there. That's infrastructure. I could see those roads, I hopped off, took the cab up here. Roads are infrastructure. I got to the hotel and I logged onto the wireless system, the wireless system is infrastructure. I drove a car here this morning. This is infrastructure. These are foundations on once you build things, right? Once you build an airport, people use it for other things. They're very expensive to build. Once you build the roads, people use it for other things. So these are just, once you build an IEEE floating point standard, a hardware standard, people use it for lots of different things. So these are just, it's a foundation on which you build things. So the term was popularized by the Stanford report. You can quibble about details, but if you don't know that baseline, shooting a little bit in the dark. So, let's see. So other possible names that report rejected were language model. These are not LLMs. These are not language models. That's too narrow, right? Because you can enter a term into a search box, say, give me a picture of a horse flying upside down with three horns out of its tail. Boom, out pops a picture, right? So there's nothing language about this picture. I mean, you took a language model, put it in a common embedding space, spit the picture out, right? So there's something going on here that's not language. Self-supervised model. I don't care whether the road I drove on was built out of dirt or concrete or blacktop. I mean, I might have been able to drive a car on it if it's concrete and dirt, blacktop and not dirt. I might have had to take a horse if it was dirt, but the road's the road. I mean, the details of the technology of how you built it, I don't want to worry about. It's still a road. It's still infrastructure that can be used in different ways. Similarly, self-supervised and semi-supervised and RIHFL. I mean, these are sort of details on how you do it, and the details may matter a lot for the particular infrastructure you have, but that's sort of specific given really the downstream goal. Pre-trained model suggests the important action happens after pre-training. There's a road there. You can use it for lots of things. I mean, you use it, but you don't have to. And foundational model, these are not foundational principles. It's just a road. It's just an IEEE standard, right? You can use it, you can misuse it. There's no claim that you're revealing deep insight into the world. Maybe concrete's better than dirt in terms of stresses, but there's no foundational principles there. So it's the idea is to emphasize its intended function. It's a foundation on which you build things. Examples include large language models, computer vision. Question, is that because they're more fundamental, or is that because there's a selection effect in machine learning for working on areas as opposed to cosmology or exoplanet discovery, where you're relatively domain ignorant? Social media, why people click on ads and enter stuff into text boxes, right? So examples are language models and so on, but there's lots of stuff in every area of science. And the question is, does it satisfy that general principle, or is it a foundational model for chemistry or inorganic chemistry, or off-shell lattice inorganic chemistry, or a off-shell lattice inorganic chemistry involving reactions of a certain form? I mean, eventually when you go down that decision tree, you have your unique problem you're working on for your dissertation. And so question, how many foundation models can there be? There can't be 10,000, maybe 2, maybe 3. But think of, you have railroads, and if the gauge is different between railroad and country A and country B, this is a foundation here, this is a foundation here, there. You can't have 50 of them, maybe 2 or 3, right? So, so there's a lot of things going by this name, but I think it's not really the original function. Now, language evolves over time. Maybe this term will be used differently over time, but just come up with a different term for what we're talking about. But for this thing that's a foundation on which you build things, I want to talk about that today. We can change the name over time, but that's what I want to talk about today. So given that name, given that concept that we're using, even if the name changes over time, can we build a foundation model for sort of scientific problems? That's sort of the question to ask. So this is how I think about exoplanet discovery and drug discovery and cosmology and theoretical computer science and theoretical statistics and stuff, right? When you talk to industry people, they have this concept of horizontals and verticals, right? A horizontal is a manufacturer that holds a certain horizontal pipeline. Maybe a distributor. I'm a distributor, I can distribute lots of stuff. I don't care what I distribute, I just distribute. If I'm a supplier, I can supply lots of stuff. If I'm a commodity producer, I might want to go invade a country or something and take it over so I can get their rare earth minerals. I'm going to use those minerals for lots of things. I distribute it to lots of people, right? So that could be a horizontal person, or I can be a vertical person. I want to build the drugs, right? I want to get oil and I want to sell oil in gas tanks or something, right? I can be a vertical person. If you're a CEO in a horizontal market and you think you're in a vertical market, you'll die because you make decisions that are wrong and so your competitor will beat you. If you're in a vertical market and you think you're in a horizontal market, so you need to know where you are. What does this have to do with scientific machine learning? So machine learning is a horizontal, right? It provides a standard sort of thing across a wide range of areas. There exist areas that use statistical data analysis in biology. It's called biostatistics. In economics, it's called econometrics. That's not machine learning. You can say, oh, they use k-means, we use k yada yada, but it's not culturally what machine learning is. It's not why you're reading about this stuff in the newspapers, right? So machine learning is a horizontal. It's like a road, it's like an iPhone, it's like an airport. You can use it for lots of things. When you do that, there may be a selection bias for working in areas that are less mature, where you're more relatively domain ignorant. Who knows why people click on ads and stuff, right? So that some of the early wins, were monetizable and stuff where you're relatively domain ignorant, but you can apply it to other areas too. Domain sciences are verticals, physics, chemistry, and that's not painfully obvious to you. It's because you don't have a degree in any of those areas, right? I mean, so these are very strong, but university departments are verticals, right? Doing stuff across departments, you'll die, right? I mean, so very hard, right? So funding structures are vertical. I mean, in NSF, and you talk to size, you talk to staff. I mean, so a lot of these institutional structures are verticals, right? So are you in a horizontal or vertical? Machine learning is a horizontal, domain science are verticals. Where are you seeing the high profile successes of scientific machine learning? You haven't seen it at Genentech or Shell Oil. You haven't seen it at AlphaFold. You've seen it in AlphaFold at Google, Facebook. You've seen it at hyperscalers. You've seen it at horizontal companies that take a bit of domain and sprinkle it on, right? That built out that horizontal infrastructure. So you don't see AlphaFold at Genentech, right? You see it at horizontals that put science on, right? So there's a tension here. There's this phrase that probably the ML people know about that I've been mentioning recently, because for the first time, it's a sort of thing that you'd say it anyway, so don't say it if it, but for the first time I heard a domain scientist talk about this. This is someone at Berkeley that was in, I don't know if it's the materials or some division at LBL, the bitter lesson. And so the basic idea, the bitter lesson of machine learning and AI is over the last 70 years, you can do one or two things. You can build out models that are forward compatible with scale and then tack a little bit of domain insight on them. Or you can cook a lot of domain insight on. And so you see, and the former is always the better thing to do if you take the long horizon. The latter is always the better thing to do if you want to get a paper into NeurIPS next year, or ICML next year, or get a product into development next year, or solve a very narrow objective, right? And so this is very obvious if you want to build this out longer term. So for the first time about a month ago, I heard a domain scientist talking about, geez, what do we have to offer than the materials and the chemistry, given this fact, right? And so I think that's a fair question to ask, right? So the high profiles of success has been seen here. ML's building this out. Domain verticals are doing that. And there's really a bit of a culture clash here, right? So we want to build out this horizontal infrastructure, maybe for scientific ML. And sort of how do you do that? And the basic reason for this is that you can cook a lot of domain insight. You saw this with text, DARPA supported stuff in the 70s. You see those images, you see this with chess, you see this AlphaGo. Now you're seeing this with science. And so the foundation model thing says, can we take a step back and use this as an excuse maybe to rethink this contract between the way the horizontal and the vertical talk to each other? So what might be possible is something that's a meaningfully scientific foundation model. I chose these particular things just because these are things we either have results on or we've been thinking about, but think more generally, right? So say that I've trained on data from atmosphere, meaning climate and weather. I'm just a humble machine learner. I don't know anything about science. So climate and weather are the same, right? The different time scales, but it's just a bunch of data you give me, right? Maybe the climate scientists and the weather scientists and their verticals think they're different, but I don't know the difference. Land, water, and ecosystem processes, subsurface, heterogeneous flows. I mean, a lot of interesting stuff going on in the subsurface, actually, because you're relatively you're relatively ignorant about what the details of the physics. What really matters is the tail structure. So think of petroleum engineering or something. What really matters is the tail structure. In most areas of engineering, you need 3 digits of precision. You're not going to fly in a plane if they're about right to 10%. Petroleum engineering is an exception, right? Who knows what the mean structure is going on in the earth, but you're interested in the tail structure. And so nominally, that's what machine learning cares about, right? The tail structure, the variance structure. And so sometimes they optimize a forward error, but can you use something like this as a way to get better principles for scientific ML? Maybe train the language models. I won't talk about that today, but clearly you can graph that on. I just won't talk about that because it's sort of an obvious thing and a lot of people are thinking about it. Can you take that and transfer learn to data from astronomy? So discovering habitable exoplanets. We had a project where people wanted to find habitable exoplanets at a pipeline. They needed a certain physical parameter, and the answer they got was 71 plus or minus 3. And you run a different pipeline, you get 17 plus or minus 8. Incomparable. The whole details depended on the analysis pipeline. Those neural networks and all this stuff, right? And so they didn't have any control on stuff. So can you get better control on that? Material science, learn physics across scales in an end-to-end way. There's a lot of people that talk about multi-scale modeling, and basically it's all clunky from the scientific computing perspective. This is what ML should do, right? Black box, chain them together in an end-to-end differentiable way and press the button. That's what the relative strength is. Chemistry, learning interatomic potentials, floods. I drove on the car here yesterday. People have car insurance. People have car insurance here because 30,000 people in the US die a year, plus or minus small variance. You can price it pretty well. Companies enter the market and insure that risk. Could you have an analysis good pricing for floods or earthquakes or fires? Right? Very relevant for Los Angeles, right? So to say that the tail events, not a Gaussian, the tail events, because there's a heavy tail in all these things, I can predict whether this is a once in a 10, never mind the climate's changing and yada, yada, that makes it harder, but forget that issue. I can get tail events right to say this is a once in a 10-year versus once in a 20-year versus once in a 30-year event. If I can price it that well, I can enter the market and create a market around that. I mean, there may be political and social issues, leave that aside, but technically you can do, I suspect that could be done, but that's nuclear physics. How much do you need to know about nuclear physics? So if you know nothing about nuclear physics, the following, you're good to go. There exists nuclei Z equals 1, hydrogen, Z equals 2, helium, Z equals 3, all the way up to Z equals 92, uranium, and then some funny stuff, right? Could I take this broad-based model that I trained up there and fine-tune it on a small amount of Z equals 1 nuclear physics data and Z equals 2, all publicly available. This data is publicly available, right? It's not easy to get at because it's in a domain vertical, but train to that data, Z equals 3, Z equals 4, Z equals 5. How far up that ladder do you need to march before you're learning classified information? Very real question. And if whoever we are, is not thinking about it, you can be pretty sure other people in the world are, right? So it's a very practical question. How is this even possible? My data is especially unique. And I think the leading order lesson is no, it's not. I mean, you're not so special and unique. Netflix and you can predict what movies you'll want to watch better than you can. So don't think your data from this vertical is so special compared to that vertical. You both live in three-dimensional time, space. You both have some interaction structure. So take a step back and look. So how might we want to build this out? And I'll give you two examples that we're not considering, but clearly you might consider it. Option one, just call ChatGPT and say, where can I discover new drugs? And a year or two ago, people used to poo-poo this and say, oh, ChatGPT hallucinates, it's all bad. Of course, you put a bit of effort in and you think about how to mitigate hallucination. You fine-tune it to, drug data and drug articles, and it does pretty well, actually. Option one actually does pretty well, if you're careful about that. I won't talk about that, but that does actually pretty well. Option two is use these embeddings to discover some other objective. So you can imagine, time series data, there doesn't exist stuff like MNIST or ImageNet. It's really high quality data for ML people that are domain ignorant to train to. Such data do exist in climate or cosmology or the scientific verticals, but they're hard to get. As mentioned, Amazon, Amazon, Walmart, supply chain systems, at finance companies, but of course that data is not released because it's valuable. So working on public time series data is a pretty low bar in terms of getting metrics. So I want to mention a result that's out now so I can talk about it. On internal Amazon data, this is 18 months ago, take a public LLM. This is internal people at the company, so they can't use the best LLM. So B minus LLM from 18 months ago. Take that, strip out the last layer, look at these embeddings. Internal goal is to predict dog food demand. There's 100 million products, predict demand for all these products, whatever, 104 weeks out, 2 years out. And you can imagine that they have high quality internal metrics that allow them, to do this, a much higher bar than the public metrics on time series data. Strip out the last layer, take this, learn a one-layer MLP. So you take the embeddings here, the tokenization, you tokenize multivariate time series for 100 million products, learn a one-layer, maybe learn a two-layer with a nonlinearity for a covariance structure. You could do comparable to internal state-of-the-art metrics. So question, what does the Wikipedia articles on which this thing was trained have to do with whether you're going to buy dog food 24 months out? So those are pretty different, right? So when you think your data is very different. Okay, so we won't talk about that, but clearly that's something we've thought about and will be compatible with what I'm talking about. Option three is understand the methodology of ML. So use this as an excuse to say, I want to understand the methodology of ML. I said on the bottom right what that is. Apply that methodology to scientific data. Multimodal data could be text, could be simulation, could be observations, could be experiments. If I have a simulation of the atmosphere, it might be three-dimensional up into the atmosphere. I have a simulation that might be going down, but the most information I have is on the surface, so I might grade it based on the surface. So now I have information on the surface, and from the ML perspective, I just see a grid of the surface and some information, flow fields or whatever. I can get the same information by a satellite looking down. The discretization is different, stuff's different, but so, it could be a simulation, could be experiment, could be observation. Incorporate these spatiotemporal inductive biases into the architecture and compute. So can we develop a foundations for that? You can imagine that just out of the box, CV and LP methods don't work so well there, and so can we get a foundation? So what's the methodology of ML? I think the leading order bit's the following: scale model size, data size, and compute so none of them saturate, all right? So that's going by a certain name these days within machine learning, which is neural scaling laws. This is not the fundamental thing, right? I think the fundamental thing is that you have these models and they're strongly correlated models that have been trained to death. And so you get very complicated correlations between things. So if you think physically, it's like an equilibrium statistical mechanics system near a phase transition. It's like a fluid dynamics system when you have energy flowing across scales and you have complicated turbulence and eddies. It's like a polymer system where it's not a random walk. It's not a self-avoiding random walk. It's a self-avoiding random walk that has alpha helices and beta sheets and very non-trivial structure cooked in by evolution. So it's a strongly correlated system. It's one data point. It's not n data points. It's sort of one data point. And so the basic thing is you have this, and this is not well suited within asymptotic statistics or theoretical computer science, because most of the theory there is formulated in terms of size metrics, scale metrics, how big something is, and I want to be a certain distance. This really has to do with the shape of the correlations across science. It's much more like a shape metric. And so I think this is the basic object. And if you happen to have access to $100 million in compute, the natural question to ask is, can I see the empirical manifestation of this in compute curves? Scale model data compute, you see that none of them saturate. But say that you don't have access to this question. Could you see empirical evidence for this? Could you take those public models and chew on them and see empirical evidence for this? And the answer will be yes. And I don't know, I'll mention this later, but it doesn't fit well within the sort of usual approach of VC type approaches to machine learning theory. But if you use ideas from statistical mechanics of learning that were sort of, I don't know, moderately popular in the 90s and sort of fell by the wayside, this is a different point in sort of model space that will allow you to ask some of these, very naturally ask you some of these things. So scale model and data and compute so none of them saturate. And this is very different than like strong scaling and weak scaling and high performance computing, right? There you have a single axis and you optimize something to death. You know from calculus that if you take two limits, you can swap the order of the limits if things are nice. You can't do it if things are not nice. And you can imagine that when you train an ML model to death, you're cooking in parameters, things are not, you've over optimized something, you can't easily swap those. So the important point is to scale these two things in a certain way, in a certain limit. It's a proportional limit in random matrix theory, but things aren't IID, Gaussian universality class. So a lot of the theory breaks down, but scale things in a very particular way. If you choose one of those parameters and you let that diverge with the other things fixed, you've saturated something. If you choose the other parameter, let that diverge with this fixed, you've saturated something. It's very important not to saturate that, because when you don't saturate that, the model can absorb new stuff at different size scales. One empirical manifestation of this might be in the eigenvalue structure of the trained models. A different empirical manifestation of it's these neural scaling. So in a sense, that'll be an important design principle. All right. So can we apply that? So we asked this in a very baby setting a couple of years ago, and this sort of appeared in a machine learning venue, and towards foundation models for scientific. We said it's characterizing scaling, although the paper worked on a tall, smaller toy model, so let's not talk about the scaling here. Ask about the transfer learning issue. So the usual thing, like on the left, is take a given, we use neural operators. You could have used neural ODEs or pins or other things like that. Take a given input, predict a given output. That's the usual way. I have a single model, I want to do that. So the question is, could I do the following? Could I train on 10 different inputs, get a base model, I'll call it a, foundation model, but it's a baby thing, and then apply it out of domain to different things. So we did this, and this is a very toy setting. So we had PD type A and B and C. They're hyperbolic and advective and all the sorts of different things. Change various parameters, right? Change the diffusion coefficient, change the viscosity coefficient. If you don't know what diffusion or viscosity is, doesn't matter. It's a coefficient that enters in a certain form factor in terms of your machine learning. If you're a scientist, you should design this thing in the right way. But if you're a machine learner, it's just a coefficient. It might be a vector. Okay, so it's a vector. It might be a matrix because of cross correlations. But give it to me and I'll train to that. All right. And so the question is, can I do well sort of in transfer learning? So this is an example of a plot you can get. So top left, I train on the parameters 1 to 5, and I test on the parameter is 2 to 3. So the outer domain's really in domain. And both of these are log scales in terms of amount of data in the new domain. And y-axis is quality, down is good. And so the solid line, what you see is when I train to 32,000 points from domain A, and then I test with fine tuning on 2, 4, 8, 16 up to 32,000 in domain B, when I start with the pre-trained model, it's the solid curve, I'm good. I'm orders of magnitude 10 to the minus 3 or 10 to the minus 4, right? If I don't have the pre-trained model, I'm pretty bad. But then as I train to 2, 4, 8, 16 up to 32,000, I do pretty well, and they touch each other at 32,000, obviously, because the first thing had 32,000, right? Question, am I cheating? Because I'm starting with 32,000 points from domain A, and then in domain B, I'm either training a new model from scratch on 2, 4, 8, 16 points, or I'm taking this model trained on 32,000 and fine-tuning it on 2, 4, 8, 16, 32 points from domain B. Is that cheating? Come on, someone's got to complain to me. So the first time I gave this talk, someone complained to me. And the answer is, I paid some number of dollars, $50 or whatever, to get the cab from the airport to here. I didn't pay for how much the road cost. That's a sunk cost, right? It's a foundation, and I exploited it. This is a foundation. So the model from domain A is a foundation. And so the right budget here is the amount of additional domain data in the new domain. Was there a question?
I guess, so in your top row, you have overlap.
Overlap. And top left, the overlap is trivial. It's in domain, but yeah, it's overlap. So the new domain is really a subset of the old domain. So go to top right, I'm training on 1 to 5 and testing on 3 to 7, or whatever the numbers are. So it's, it's slightly, but not so much. And what you see is it gets a little bit worse, but still the two things go down and pinch each other. But qualitatively, domain C, actually, I'm training 1 to 5 and testing on 5 to 10. So it's out of domain, but you might imagine 4.9 and 5.1 are not so different, but a little bit worse, they go down. Bottom right is training on 1 to 5, testing on 10 to 20 or 20 to 30, right? So not obscenely out of, but out of domain. Scientists are surprised that this got anything. As a machine learner, you may or may not be surprised, but scientists are surprised you got anything. But you do. You're an order of magnitude better when you work with a pre-trained model. Both curves go down and they don't touch each other. Neither saturates. So this figure plus a bunch of ablations and stuff, this is the babyest version of something where we don't saturate, right? We're doing something neural scaling like where I'm out of domain enough that as I feed the new data in, I don't actually saturate something. So this is actually bottom right's a very interesting plot. Yeah, question? So you said, what are the numbers on the top row? Would that be cheating? The numbers don't matter. I trained to some pre-trained model, 32,000 here, 100 gazillion on something big. And so the question is, I take a small amount of data, 100 data points, and I train a model for the universe on those 100 data points. Or I take this big pre-trained thing and fine tune it to those 100 data points. So I'm taking an LLM and I'm training to medical data or text data or any data. I'm not starting from scratch. I'm taking this publicly available or not publicly available LLM and fine tuning it. So the 100 is fine tuning. So either I start from scratch or I fine tune. And whatever this 32,000 in this example or 100 gazillion in some other examples is a sunk cost. Does that make sense? And so the notion of 100 is 2, 4, 8, 16 up to 32,000. So the only cost here is the amount of additional data from the new domain, which in these 4 plots, one of the new domains is intra-domain, overlapping, not overlapping, and quote, very outer domain. Make sense? Okay. All right. A bunch of other plots to justify things. These things saturate and don't saturate in ways you might expect. So, all right. Lots of open problems go beyond the toy thing, go to 2 or 3D. We applied it to neural operators, apply it to other things. We're looking at some of that, self-supervision and preach. So a lot of things that are the obvious questions we're looking at, and I think we're reasonably robust to those. All right. So there's a bunch of scaling stuff. I'll have a little bit to say about that on implementations later, but you can imagine industries running ahead with that. People want to scale. The general principle of taking a pre-trained model, a toy one, transferring to outer domain data, this and a bunch of other examples like that I didn't show, works well in toy situations and well enough to surprise domain scientists. I don't think most machine learners have been surprised, but well enough to surprise domain scientists. So I'm a domain scientist. I want to cook in a lot of domain knowledge. Will that help? So the TLDR is that it can, but that's only the 10th way you try. The previous 9 it won't. It'll break. But, that's not quite true, actually, because if your goal is to get a paper in to ICML, actually, what's the next deadline? It can't be ICML. It's NeurIPS. Okay, so we have 5 months. If the goal is to get a paper into NeurIPS, don't follow this. 6 weeks. Okay, so whatever you do, if you have 6 weeks, don't follow my advice. Do the opposite. But if you want to get something longer term, follow my advice. So so there's a class of models known as PINs, physics-informed neural networks. They take an objective and tack on a physical regularizer. The physical regularizer is the spectral norm of the differential form of the diffusion of the operator. When you tack on a regularizer machine learning, it's a ground ball, like an L2 ball or an L1 ball. It's not derivatives, differential form. Derivatives are choppy. That has a non-trivial null space. And that null space depends in a complicated way on viscosity or some other coefficient that might be changing in some way I can't control, right? So tacking on this regularizer is very intuitive, but very different than the way you do it in ML. So the short answer is you can do this. ML has so many knobs. Fiddle with the knobs long enough. It might take 8 weeks, so you might have a problem with the nerves. But the next deadline after that, fiddle with the knobs, you'll get a positive result. And that positive result, if you change any of the physical parameters, will break. And it won't work. So it was well known that these are a little bit finicky. One of the first papers we had in this was something that Aditya and Amir had, characterizing possible failure modes. And it basically said, just do this and it'll break, right? There's lots of ways to fix it. And if you're a smart engineer or a good scientist, you figure out those ways and fix it. But all those ways are just orthogonal to what ML is doing. And so lots of failure modes. And we just identified that and pointed that out. And it's gotten a lot of attention because everyone knew that, right? So 6 months later, we didn't have to beat the bushes. CACM put up an article, and this is one of these things I discovered about articles in CACM. It sounds like a good title, but the title, if the title's negative, no one reads the article. The title has to be positive and aspirational. So neural networks learn to speed up simulations. That sounds like a good title. The interesting stuff is in the subtitle, which says physics-informed machine learning is gaining attention, but it suffers from training issues. And just to be clear, issues is a euphemism there. So it suffers from training issues. And so, we want to identify those issues. So why is there's a lot of ways to incorporate physics and machine learning into ML. Most of them are a little bit clunky because you either start with the ML and graph the physics on afterwards, or you start with the science and graph the ML on afterwards, like this differential form, the regularizer, and then it breaks. So soft constrained, soft constrained pin models fail to learn relevant physics. Really what you want is a hard constraint. It's not as simple as hard constraint versus soft constraint, but the methodology of machine learning doesn't know the difference, right? It says hard constraint, relax it to the Lagrange dual. It doesn't care about the Lagrange dual per se, but the form factor of interaction is press the SGD button. And when you press the SGD button, indirectly, you're getting this Lagrange dual form factor. And so indirectly, you're not solving the hard constraint, you're solving the soft constraint. And these two things are non-perturbatively different because you have a singular perturbation. Just think ridge regression versus Moore Penrose, right? Ridge regression takes a small singular values and blows them up. And so, the very, very small ones at machine precision become very large. So you have this non-singular perturbation. So same thing going on here. If you like to think of it in terms of loss surfaces and optimization landscapes, being not very, very careful of this, you totally mess up the loss surface. You go from something relatively smooth to something that's very choppy. Think of it like a stiff differential equation, fast scales and slow scales. You get lots of fast scales that just mess you up. But it's in these scales that are non-physical, but reasonable ML parameterization space. So, all right. So foundations. So is it possible to fix these things, right? So, let's see. Here's just one example. I like this one because it addresses that pin thing. And I'll give you some other examples. So we had a result, and we said, this is the sort of thing you can be a PDE person and like it and know nothing about statistics, or you can be a statistics person and nothing about PDEs and like it. So it's really something that sits right between those two. So we call the prod conserve, roughly compute mean and variance estimates. It could be a GP. In the paper, we use something called an ANP, a certain neural process that gives you a mean and variance estimate. It could be just take a neural network model that gives you a forward point estimate, run 10 or 20 of them, get an empirical estimate of the variance, right? And then update the model. Number 2 says with an oblique projection, depending on the heteroscedasticity structure. That's the interesting piece. And it's good for sharp discontinuity. So we applied it to a GPME, a generalized porous medium equation, which is a nonlinear PDE, but sort of looks morally like a linear one in the relevant regimes of interest. It has a parameter that goes from nice to not nice. Nice is the left there. It's a bunch of smooth curves. Not nice means that you have a transition where the function is continuous, but the derivative is not. Very not nice, the function is not even continuous. And so you can imagine I'm talking to you, the speed of sound, the waves move, boom, and you hear me. But if I'm a supersonic jet flying at 800 miles an hour, you'll never hear the sound coming. The plane will hit you in the face before you hear the sound because the plane's traveling faster than the sound can travel in that medium. And so you're going to get a sharp discontinuity in that sound profile. So think of that as what's going on. And this appears on this sort of fluids. It appears in sharp constraints. If you're interested in a sharp physical constraint, it appears in conservation laws where you want to satisfy energy, something. So all of these things under the hood are the same thing. It may not be obvious, but they're the same thing. And so what you see here is that when things are nice, the heteroscedasticity is pretty uniform. Take the model, you violated the constraint, do a projection down, the obvious orthogonal projection, things good, you satisfy it. There's a question about training versus tests, et cetera. But when things are not nice, and in particular here, this shock position thing on the B on the right, when things are not nice, I want to find the shock profile here, but there's a sharp transition there. So take this an estimate and do an oblique projection. Right? An oblique projection is still an idempotent operation. It's oblique, it projects down at an angle. And then when you apply it a second time, you stay in the same subspace. So it's an idempotent, it's a projection. But the obliqueness matters because the heteroscedasticity structure says downweight these things where the variance is bad and upweight these things. If you do that, you pull that purple thing, you pull the estimate right onto the position. Question, can you do this in an end-to-end differentiable way? Question, can you do this with more complex geometries, et cetera? So answer is probably yes, and we're looking at each of those. So this is nice because it actually takes the integral, something I didn't mention, it takes the integral form of the operator as a regularizer, which adds a certain robustness, and then it post-processes with this thing. You can know nothing about PDs and just statistics and say there's a non-trivial heteroscedasticity structure that we dealt with after the fact. Or you can be a PD person, in which case they couldn't even say the word heteroscedasticity, but they'd say, yeah, obviously at that shock position, things are bad. Right? So a bunch of other things. And let me just walk through a couple just to give you a hint of something. But a lot of these actually sort of are a little bit get into the details because it's a foundation, right? The details of not just pressing the SGD button, but getting a little bit into the details of what's going on. And a relatively good model. I mean, I did a lot of work in spectral graph theory and randomized linear algebra. And so randomized linear algebra is interesting because it's right between the theory of algorithms and high dimensional statistics and machine learning and applications. And the applications, some are scientific, but some are machine learning, neural networks, and then the latter didn't exist years ago, basically. And so you really need to think through a bunch of little careful things. And I haven't seen any other area that's, I mean, a lot of it, you probably think of it's a little bit of a snoozer, and I won't disagree, but they actually do a good job on addressing the following question. I have a discrete thing. What does it mean that it approximates a continuous thing? So mathematically, that doesn't make any sense, right? Discrete and continuous are sort of categorically different. When you have an underlying geometry, one answer is, I squint at it and look about the same. There's a lot of methods of machine learning that tell a story like that. I have an underlying manifold or something, but there's sort of a bit of a gap. You get upper bounds and worst case bounding theorems, you get whatever. So it doesn't really answer that question in a scientific sense. Numerical analysis does a good job of that. Basically, they say, cut the distance in half, cut it in quarter, something should converge, right? One, and two, if you think about numerical analysis versus the universe of problems you could solve in theory of algorithms, what you do in scientific computing, and I'm just using numerical analysis as an example, what you do in scientific computing, you basically say, I'm not going to consider every problem in the world. You come to me, I need the problem to be well posed because I want to make a scientific statement. If the problem's not well posed, any answer I give you won't be robust to someone sneezing on the other side of the room. And so you need to change the problem. Give me a well-posed problem, and I will give you an answer to that. So I'm not solving every problem in the world. I'm working with well-posed problems. And for that, I can get very strong results. That's very different than database systems and CS theory, where you have Turing machines that can solve everything. It's just function approximators, and you don't have this notion of posedness, right? So they address that question, and I think a lot of the things here boil down to that. Traditional versus modern UQ, weight diagnostics, and some time series stuff. So neural ODEs, there was a lot of interest a couple of years ago. Neural ODEs are discrete Euler discretizations of a continuous differential equation. Is that sentence true? Is it meaningful? What does it mean? And so syntactically, if you look at the structure of the model, it looks a little bit like an Euler discretization if you set the time step to be 1. So what machine learning would do is set the time step to be 1. Why not 2? Why not 17? Set the time step to be 1, and then fiddle with all these other parameters. And so, question, when you do that, do you get something that's a discretization of a continuous dynamical system? And the way to answer that is to have a numerical analysis convergence test that says, train here and test on timescale 2, 4, 8, test on timescale half, quarter, eighth, and see if you converge. So the bottom, the right on the top, A, Euler-Net's just a block. That's whatever's going on in that block. B, that middle thing shows that there's a big dip. Those are log scales. There's a big dip there. Down is good. What that says is that if you train on timescale 1 and test on timescale 1, you do great. This is a great discrete model. If you train on timescale 2, 4, 8, or half, quarter, eighth, you die. This is a log scale on the y-axis, so you do terribly. I mean, it's continuous in the sense that you can formally enter a number, but it's a terrible continuous model. If you say, well, I'm going to work with midpointer RK4, which in ML language is a way to chain together these Euler blocks in just the right way that gives you an inductive bias to be smooth over time, right? Numerical analysis, it chains together those blocks and chooses the parameters coupling those blocks in just such a way to cancel higher order terms in the Taylor series. So there's a picture of it. What you see is the bottom row in the middle, RK4 net convergence test. This thing goes down and levels off, solid line, and it levels off to 10 to the minus 4 or whatever. In traditional scientific computing, this thing would go down and level off to 10 to the minus 16, which is machine precision. Now this thing goes off and levels off to 10 to the minus 4, which is the basal level of noise supported by the data and the ML system. But the point is that it goes down and levels off and doesn't get worse. So this passes the numerical analysis convergence test. And depending on what you can see, the bottom left shows that by a bunch of other downstream metrics, it does well in terms of subgrid resolution and forward prediction of time and so on. We talked about this in terms of neural ODs. Same thing holds for Cindy. Same thing holds for a lot of other models. And the basic reason is you do something physical, you graft it onto ML. ML doesn't know the space and time here. It messes stuff up. So you cook something in. The interesting thing is here, you actually do better on training cats and dogs in a certain sense that I'll probably not have time to get into. So even if the data doesn't come from an underlying continuous dynamical system, this gives you an inductive bias to be smooth and more robust. So say that I train a ResNet 1, 2, 3, 4, 5 up to ResNet 200 or whatever. What does the ResNet 50 have to do with the ResNet 51 or the ResNet 100 or the ResNet 25? Can you view one as an approximation of the other? And this could be relevant because you could train a family of models. I just want to cut the number of layers in half because my phone has a certain structure and your phone has a different structure. And so you might want to do post-processing. You do better by using this idea just on cats and dogs because you get a robustness over the depth of that thing. So you can use this for scientific ML, but you can apply it back and use it for other sort of things also. Traditional and modern UQ, uncertainty quantification, a lot of you probably know, I mean, if you deal with if you deal with least squares and you're dealing with a tall thing, textbook page 101, there's a bias variance trade-off and you get this U shape. And so a lot of you have probably seen, there's this notion that if you take least squares and you look at least squares, you get this U shape. And it's maximally bad when you're square. I mean, this bias variance thing diverges. But then if you become over-parameterized and you ask for a minimum norm solution, it gets better and better. And when you get to very rectangular the other way, depending on the details of the model, oftentimes you're better than that sweet spot on the bias variance trade-off. Right? So you see this for least squares. You don't see this for random forests because random forests are a class of models that can't go to the over-parameterized. You cut stuff and it stops and you can't go to the over-parameterized regime. You see this for modern neural networks, whole bunch of state-of-the-art things. And so I remember, I think I was at Caltech the first time I heard it. Misha was giving a talk and I talked to him. And I didn't know this, but it didn't surprise me that something funny was going on. And the thing that surprised me was that the ML community was so surprised. So this is a community that works with certain types of theory, always in this tall regime, the least squares regime, general linearized models, lots of bells and whistles. Page 1 of the regression diagnostics book says more data than parameters. Let data diverge. So they should have no more of an informed opinion than some random person off the street. What happens when you go to the other regime? The theory goes through scale metrics, not shape metrics, and it's always in the one regime. Why would you have an informed opinion over here? So the whole community was surprised by this, and so the TLDR is that you work with under-parameterized models because you're a scientist and you want to do a big GP. Good. You want to graph that onto a big neural network that's over-parameterized and has lots of other moving parts. Good. Put the two together. What do you think is going to happen? Are good things going to happen to good people or bad things going to happen to good people, right? So there's a whole bunch of interesting questions. It's not just in the forward prediction error, but the uncertainty structure behaves the same way. So you have all these intuitions about log likelihoods and stuff. In some cases, they correlate with what's going on in the over-parameterized over a parameterized regime. In some cases, not. So you have a bunch of results on monotonicity and double descent with GPs in this case. That's a linear baby version of what we call an interpolating information criteria. So if you're a statistician, you like information criteria. There's a bunch of information criteria. All of them are only relevant in the case we have more data than parameters. Can you say anything more than 0 but in the other regimes? The short answer is yes. The long answer is, I guess, talk to me afterwards because we're running out of time. But I think UQ is a first-class citizen for a lot of these scientific ML things. And a lot of ML people are thinking about calibration and are thinking about non-robustness. And this is a great playground to figure those things out because you can ask scientific questions of it in a way that you can't ask ChatGPT, right? I mean, so you can ask well-defined questions. You get answers here, you can feed it back. Exactly analogous to that numerical convergence test. We developed it here for the continuous system. It's just better for ResNet and cats and dogs. All right, a whole bunch of stuff in time series. Let me not get into that just because I think time series is a whole sort of can of worms that pretty interesting, but let me not just get into implementations. We're putting a bunch of randomness into LAPACK with RAND BLAST and RAND LAPACK. Which I like this plot because the plot on the right, I think it's this one, basically shows the size of the model and the size of the GPU limit. And so as this thing goes, the x-axis on the right here is basically time. As the size of the memory goes up, all the models get bigger. And so this is like someone that just can't stop eating candy bars or something, right? So the memory goes up, models get bigger. Memory goes up, models get bigger. So so how do you deal with better tokenization and quantization and so on? And if you do all these things after the fact, does it mess up all the other stuff we're talking about? So we're doing a bunch of stuff there. Applications, we've done a bunch of things. And I'm happy to talk, I'll be talking to some people this afternoon. So there's a couple of different ones. The particular tactic we're taking now is look at the text less. A lot of people are doing that. And focus on something where there's a particular technical edge, which will have to do with basically simulations, figure out some of these issues, and then wait a year or two that the text people would be more mature. A lot of people would be more mature, and so can we do this? So you have a super resolution benchmark. How do things perform when you go to subgrid resolution? When you have nice, smooth flow, things break. I showed you the example there. When you train on timescale 1, test on timescale half, things break. So even when things are very smooth and nice, never mind turbulent flow, which is much worse, right? So how do you control capacity in a turbulent regime and so on? So there's an effort we have that is DOE funded in this case from Oscar, where we're basically saying, in spite of a recent effort, there's no scientific foundation model, in the sense that I used the term earlier, that's been trained on a broad range of data. So there's a bunch of things going by that name if you do a web search, right? But it's all in one domain, and so it's a large pre-trained, but it doesn't transfer in the same way. So it's been trained on a broad range of data across different domains to gain an understanding of multiple physical processes. They had a call to say, we want to develop a foundation model. We sent in a proposal and said, you can't, not on the timescale and budget you're offering. So we're not going to propose that and lie to you. What we can do is sort of get a detailed blueprint of what you might expect, right? So, so that if you want to make further investment later, you could. And the detailed blueprint would basically be identify the pain points, a bunch of stuff I've been talking about, and get a sort of a plan forward. So the three main technical challenges I think block the development are the lack of neural scaling with respect to model data and compute, but also space and time. Lack of control and out of distribution. Out of distribution, has a slightly stronger semantics than a lot of these scientific applications, but it's also a good stress test, right? If I'm a hammer, I like Hessian inverses and Hutchinson and these things, right? And I can stress test it on you in your climate science domain. Probably a lot of the learnings I get there will apply back to you in your language domain. So, so think of it, I can stress test these out of distributions in a much stronger sense. Lack of broad-based multimodal data. So we're going to adopt the methodology that ML people do, scale model and data and compute, and see how it performs. So there's a bunch of things that we're looking at here. We actually, one of the first results we had out was an early, convolutional, tack it onto a long memory model. We could have sent this to an ML venue, but the seismologists liked it enough that we sent it. It's under review at Nature Communications on early earthquake warning detection. About a month after we had it out, I was sitting in one of the offices in Berkeley, and this thing started buzzing. There was an earthquake in Northern California. It wasn't our thing. Our thing was still too much of a prototype, but we got buzzed. And so I asked the seismologist how would our model have picked that up. So early earthquake warning detection system, a bunch of other things. So there's a bunch of different scientific tasks, some temporal forecasting and space and time, some inversion and imaging, the exoplanet thing, like you're looking at something on the other side of the universe, just at the surface. Can you understand what's going on deep inside the surface? The way scientists would do this is do a big, expensive Fourier transform and go to very high frequencies. Can you have an ML model lift to a non-physical place, get some good inference, go back and do high frequency inversion. And this is medical imaging, this is exoplanet discovery, simulation to real transfer. So there's a bunch of things where you can learn across scales. And that's, I think, where the ML will have a lot of scientists want to fix this particular box. And culturally and technically, there's no way the ML has an edge here. But if you take these boxes and chain them together in some way and learn across scales, that plays well with the neural scaling and it plays well with ML. So a bunch of stuff looking forward. I think I'm sort of almost out of time. What are foundation models? Is one word. What's the foundation models? It's a foundation. It's infrastructure. It's a foundation on which to build stuff. People do stuff with IEEE floating point standard and iPhones and roads and airports. Can you do the same thing for scientific ML? I think it's tricky because if you're a scientist, you care about this vertical. I'm not going to help you, right? But if you can solve something on the horizontal and solve 2 or 3 verticals, it will help you. So there's a challenge here, but I think this is a way to give scientific ML a good, strong, robust principle foundations. And if you happen to be a theory person that doesn't care about this but wants better theorems, under the hood here, there's a lot of those too. So I'll tell you about those if you grab them later. All right, thanks a lot.
Question about transference part using the foundation model. There are also examples where you transfer the foundation model, comparing the training from scratch and training from scratch is actually doing better, and foundation model is hurting you, in terms of getting into the correct model.
Yeah, I'm sure there is. I mean, I'll say yes, but it's hard to answer that question in the full pipeline because you got to do a fairly detailed thing to show why the result didn't work. And the first 10 things are just because you were stupid and didn't train properly, whatever, right? I don't have a good sense of the interface where state-of-the-art training, state-of-the-art whatever, the foundation model would hurt. I could imagine there's cases where there's too big a delta between this outer generalization, and basically I have some coherence in the concept class, to use the buzzwords, but if you press me what precisely I mean, it's a little hard to. And grafting this onto the foundation model, and fine tuning, basically I'd adjust the weights, and so all the sort of math gets sucked up here, and so I do worse here. I suspect there'll be examples like that. I also suspect that where there's examples like that, if you wanted a positive result, you could fix it in some reasonable way. So I don't have a good sense of that sort of boundary, but yeah, but we certainly see it, but I don't know that it's such a real thing. I mean, think of the road example, right? You put a road in the middle of the city, that has downstream consequences, right? I mean, it literally puts a road in the middle. People live here, people live here. So it definitely will affect the ways model get developed. So there's certain things I can't do. So that'll be the case here too. And so you're asking if there's certain things that are made more difficult, and probably there will be.
Probably is a good example. The example I have in mind is riding a bicycle. If you learn to ride a bicycle first and then try to ride a tricycle, you realize you can't actually do it, right? But if you don't have that foundation knowledge of riding a bicycle, you ride a tricycle and everything is automatic.
Yeah, there may be examples like that. I mean, I think you could probably ask an academic question. Where's the boundary between where you can fail? And there's probably some outer domain thing, or if it's close enough, I could learn to ride the tricycle or not. And then there's just a question, this is the way the world's heading, and do we need tricycles? So yeah, so I don't know. Yeah, I think I don't know of a good place where that question gets either an academic place where that question gets asked, just given the values of ML and the scientists and so on, or an industrial place where that question gets asked. Because if it looks like that, the industrial people just jettison that and work on this. But if there was a place, I mean, it would be interesting to see. I just don't know.
Yes, follow that question. So if you want a foundation model to serve as a foundation, you need a stable interface with the downstream tasks, right? If you improve your foundation model, you don't want an interface to change this problem. So how do you see that coming in scientific machine learning foundation?
Yeah, I don't know. So I think people use it in different ways, and there'll be some people who want to use it in a very superficial way, and then there'll be some medium people and then some power users. Some people want to talk to it in a language interface, and for that, just look ahead. The language models are going to get better, graft onto that, and something will happen there. There'll be some people who want to be a little bit more technical, think of it, I want to do time series forecasting, and what I can do is use Excel. So I don't have to use natural language, but I can do something. I don't know if Excel counts as a language or not, but something that people use. And so it's a little bit more formal than a language, but and so I could interface that way. And then there's power users, that use Python or Fortran or C or something. And so they could get much more into the weeds. And so I think for each of those, having an interface that it doesn't change dramatically a lot. And so clearly the dynamics of different groups would be different in those cases. But for a bunch, I think people are thinking about it in terms of the language interface. We just have thought about that less because it seems like everyone's thinking about it, but I'm sure that could be solved. And then there's a cultural thing about, I'm assigned to an area A, you're in area B, and I have, PDE code of type A for solids and you have it for liquids, and those are very different, right? We got to go back up the food chain to something very high, the provost to get to a common ancestor and so how does that interface? Could I get a common interface between those two? That seems like an interesting thing to really deliver on the foundation for the science, because then I could draw strength from what you have and what I have in a unified way. And that's, I could imagine that, but that's a little bit, I don't view that as primarily a technical thing, right? Because you could imagine developments in language models, and I fine tune it to scientific data and high quality code, not just Python code that's up for homeworks. And it does well on yours with a bit of fine tuning in mine, and then they talk to each other. But that's at least as much of a cultural thing as a technical thing. So
have a foundation model for data modalities like time series only, like a single, because even in language or vision, you have a so-called foundation model. They all build on the same model architecture, like for the transformer based, right? Further, reverter, and all the same type of architecture. And in time series and spatial temporal, people have shown that for single modality time series, like transformers don't work, right? So do you think there is, even there's a basis for foundation?
yeah, I mean, that's a good question. I don't know. The leading order thing in all this is get the spatiotemporal right. I mean, the delta and what I talked about between general foundation models and scientific is basically spatiotemporal, because in as weak a way, in as strong a way as you can, in as weak design principles as you can. I think the time series is a good example because, there's a book, Statistical Mechanics in One Dimension. Every problem solved analytically. In 2 dimensions, no problems solved analytically except one that I'm talking about the Nobel Prize. Right? In 3, nothing solved analytically. I mean, so you use simulations or perturbative, range of things. 1 dimension, and think about it in terms of algorithm theory. I mean, look at all the possible metric spaces you can have. 1 dimension, and if you're doing algorithm theory, it's discrete, but also the real line. 1 dimension is an incredibly special metric space. I mean, incredibly special. The duals, complete graph, yada, yada. And so why does a transformer work? Why does an LLM work? I mean, it doesn't seem to me there's anything particularly language about it. It's more like this recursive structure and this autoregressive structure. And if I had to guess, based on the time series thing I mentioned where we did this, learn the mapping and some other things, if I had to guess, the reason these things are working is because 1 dimension is an incredibly special metric space. A common metric is compute budget. And so the transformers give you a way to do a bunch of stuff in parallel relatively easily. And so you're working in a 1-dimensional metric space. And so these things are learning 1 over F noise. So they're not an autoregressive 10 process where you see back 10 steps. They're not a process where you see the whole history equally. It's sort of like a heavy tail process where you learn the last 10 steps with constant fraction of your attention. I don't know if it's not technically, no pun intended. The last 100 steps with constant fraction, the last 1,000 steps with constant fraction. And so it's not Fourier series where you keep the top 10 Fourier modes and that gets the high or low frequencies. It's more a model which, coupled with the computational benefits of it, allow you, because it's a 1-dimensional structure with tokens, allows you to learn 1 over F noise. And so that means that it seems like it should be relatively easy for time. It should be easy for 1-dimensional physics, but of course, every problem solved analytically. The question is, can you extend it to 2 or 3-dimensional? And so there, I could imagine you do something where I want a Green's function, which is like a resolvent, and I propagate information in from the boundary, and then I grade levels of boundary by the radial coordinate, then I have the angular coordinate. And if I can grade this in by the radial coordinate and push mass in, I could imagine that. So at a minimum, there's a bunch of interesting results there. Whether this changes the world, you come back in 3 years and I could, but it doesn't seem to me implausible, right? I mean, because there's a bunch of clunky ways that scientific computing, very sophisticated, but 2 versus 3 dimensions and this boundary condition versus that. And so, it's not obvious to me that the answer is no. I mean, and 3 versus 2 is going to be very different in terms of its isoparametric properties, which has to do with sort of the way the statistical methods can cohere, you know, inference and stuff.
I guess we're out of time, but yeah, you can take the questions off. Yes, thank you.